So we have here a double sheared joint, and to put things into perspective, I'll just zoom in so you can see. So what you're looking at here, we have two connecting plates above and below another. So we have this one here in the middle, and then of course above and below that one. And what happens in this type of joint is we have two sheared planes for each bolt. So you can see where there is a tendency to cut across the bolt in that area highlighted in red, and then come down here again, we have another sheared area. So across the bolt we have two sheared planes, and what that tends to do is it gives us actually an advantage because it actually distributes the forces across a much bigger area. So if we look at that from an analytical perspective, if we know that our area is equal to pi times the diameter squared and divided by 4. But because we have two sheared areas, we're going to multiply that by 2. So 2 times pi d squared divided by 4. And of course, if we have the number of rivets as well, then we can also include that. So what we can see is this version of the formula where if we were to just reduce this to cancelling down that 2 divided by 4, we end up with pi times the diameter squared and times n, and instead of dividing by 4 here, we're now dividing by 2. And if we were to then couple that with our stress formula, what that will look like, so where we have stress equals force divided by area, if we were to use that same formula for area, then what that will give us is force divided by, and we have the pi d squared times n over 2 in this instance. And if we were to just do the inverse of that, then we end up with 2 times force all divided by pi times diameter squared and times n. So this would be the formula that we need to calculate stress. So we can also rearrange this to find any of the variables, and that's exactly what we're going to use now for this question. So what we have two steel plates that are riveted together, and they are using 16mm rivets. We have the factor of safety right here, which is 1.5, and we also have the ultimate shear stress right there, which is 50 megapascal. And what we're required to do in this instance is to find the safe working load. So we're going to apply this now. So I'm going to break this down step by step first without using the main formula, so you can follow as I'm going through. So the first thing that we need to find out is the area of, let's say, a single sheared plane or a single sheared area, and that will just be pi times diameter squared divided by 4. So we already know what the diameter is, so that's going to just be pi multiplied by 0.016 squared divided by 4, and that will give us an area of 2.01 times 10 to the negative 4, and that's meters squared. But what we know is that the bolt is sheared across two areas, so we then have to multiply that by 2. So we're going to have to then double that area. So that will just give us 4.02 if we multiply that by 2 times 10 to the negative 4 meters squared when we double that area. So that's the area across the two sheared surfaces for the bolts. Now, just before we go any further, I am very passionate about growing this channel and putting out as much valuable content as possible, and I would really appreciate it if you could just support by subscribing to the channel and liking this video. So back to the calculations. So the approach I'm going to take this time around is just to use the maximum stresses, the maximum forces, because we do have those. And what that will look like is if we think of our stress as force divided by area, but in this instance we're using the maximum stresses and the maximum area. So this is the maximum stress, or our ultimate shear stress. This is going to be the maximum force that the joint can take, or the maximum load, and this is the maximum area for each bolt. So what that will look like then, our force will just be the maximum stress multiplied by the maximum area that we have for each bolt. So that will just give us a grand total of 50 times 10 to the power of 6. And where we got that from, that's the 50 megapascal that we have there in the question. And the total area that we just calculated was 4.02 times 10 to the negative 4. So that's 20,100, and we can be flexible with our units. We can say that's newtons. And then now, if we were to find the safe working load, we can just divide that right there by our factor of safety. So if we say 20,100 divided by our factor of safety, that will give us 13,400, because that's our safe working load now. So the maximum load it can take is 20,100, but when we divide that by our factor of safety, we get 13,400. Now let's try to get the same answer using the previous formula that we had. And that formula was stress equals to 2 times our force, all divided by number of rivets times pi times our diameter squared. And the stress that we're looking to use here is our maximum stress. But in this instance, it's going to be in relation to our factor of safety. So if we look at this formula that says factor of safety is equal to ultimate shear stress divided by working stress, or our safe stress in this instance, not the maximum stress as we used up top, but our safe stress. So finding our safe stress, we would use our 50 times 10 to the power of 6, and that's representing our ultimate shear stress, divided by our factor of safety of 1.5. Now that's going to give us 33.33 times 10 to the power of 6 megapascal. So that's the stress that we're going to use in this formula this time around. And what we hope to get is our 13,400, just as we did before. And this is just to show you another method that you could have used. So if we were to rearrange this formula now to get our force as the subject, then our force would be equal to stress times number of rivets times our pi times diameter squared divided by 2. So if we put all of that in now, then our stress, 33.33 times 10 to the power of 6, it's 1 rivet times pi times 0.016 squared, and divide that by 2, and what we end up with is 13,402.8 newtons, and that's pretty much the same as what we got before. It's slightly different by 2.8 because we have used different rounded values, and that's why it's slightly different, but it's exactly the same value really if we were to round using the same digits. So that just gives two different approaches, and either one is just as good. So hopefully you found value from this video, and please subscribe to the channel, give the video a thumbs up, and I'll see you in the next one.